approximate the value of y equals square root 4 plus sine x at x equals 0.12 obtained from the tangent to the graph at x equals 0. So to do the tangent line, to do the linear approximation, you're basically finding what you've already done, which is the tangent line. They give you this kind of overly complicated formula here, which I'll snip in, but really you need a point and a slope. Okay, so your point comes from putting x equals 0 into the function. So 4 plus sine of 0, which ends up being the square root of 4, which is 2. So you got your point. That's your x0, and that's your y0 for the formula there, or f of x0, I guess is the way they're doing it. Is that okay? Clear?
Wait. Okay, x0 equals.
We're putting 0 into this y right here.
Okay.
Sine of 0 is 0, so it's just the square root of 4, which is 2. And they're using different notation. They're using, they like to use x0 or x0 instead of x, and then f of x0 is really y. Is that okay or not?
Yes.
All right. F prime is derivatives. The second thing we need is the slope. That comes from the derivative. So you got to find the derivative y prime. You may want to rewrite it, I guess. I just got a sense last night the derivative rules you hadn't done in so long that they weren't real clear. So a rewrite step here, you're going to write 1/2 power rule. This is power of 4 plus sine x to the minus 1/2 power times the derivative of the inside function. Derivative of 4 is 0. Derivative of sine is cosine. And now you have to evaluate the derivative at 0, at whatever the x value is. So we have to find y prime of 0. 1/2 4 plus sine 0 to the minus 1/2 power times the cosine of 0. So the sine of 0 is still 0. 4 to the minus 1/2 power, that's really 1 over the square root of 4. Cosine of 0 is 1. So this becomes 1/4 is your slope.
And
So
that would be.
That's the f prime of x0 or x0. That's what this is down here.
So x of 0 equals 0. So you plug in 0 to the derivative?
Yes.
Okay.
So now your tangent approximation is 1/4 x minus 0 plus 2. And then you could be asked for the equation, but here they want you to put the value of 0.12 in for x. They want you to actually evaluate it at that point. So L of 0.12 equals 1/4 times 0.12 plus 2. 1/4 of 0.12 is 0.03 plus the 2 is 2.03 or letter B.
Okay, yeah, that makes sense.
Example 2 is very similar, except they're not giving you a function. They're giving you enough information though to write the tangent line. So it says here, let f be a differentiable function such that f of 3 equals 2. That's your point. F prime of 3 equals 5. That's your slope. If the tangent line to the graph of f at x equals, if the tangent line to the graph of f at x equals 3 is used to approximate to 0 of f, that approximation is, okay, we're going to write the linear approximation again, just like in the previous problem. Okay, so your x0 is 3 and your y0 is 2. That's the point. Your f prime of x0 is 5. Is that okay?
Yes. But wait, where does the y0 even go? Like, why are you writing
Oh,
that?
sorry. They're not using that. They're not. They're using this other notation f of x0. Sorry. Which is y. But yeah, it's that. So 5 times x minus 3 plus 2 is the linear approximation. Okay. But this time they want something different. They don't want you to approximate at a point. They want to know where the 0 of the function is. So they're asking you to set the function equal to 0. That's what that green part means. And
So
then
so the whole thing.
yes.
Okay.
Yeah. So, many ways to do this. I'll distribute here 5x minus 15 plus 2 equals 0. That's 5x minus 13 equals 0. Excuse me, x is 13 over 5, which is 2, and 3/5 or 2.6 letter C.
Okay.
So those are the two tangent line approximation, linear approximation examples. Then your instructor moves to L'Hopital's rule.
Okay.
So is that sufficient, or do you want us to do another?
Yeah,
Okay. All right. Okay, so the next problem here, and you might feel like you're going back in time. You're like, why are we doing limits? I thought I was done with limits. But this is L'Hopital's rule. And it comes from what is called indeterminate form. So if you recall a long time ago, when you put 0 in for the top, you got 0, sine of 0, 0, 0 on the bottom. This is one of the indeterminate forms, 0 divided by 0. There are others. Infinity over infinity is the other one that you'll see. So what do? Well, you take the derivative of the top and the bottom separately. So you don't look at this as quotient rule. You just take the derivative of the top. The derivative of sine is cosine. The derivative of x is 1. And then you try again. You're like, okay, let me see if I can put 0 in for x. You can. The cosine of 0 is 1. 1 divided by 1 is 1. So the idea,
all you do?
Yeah, the idea is if you get indeterminate form, you take the derivative of the top and the bottom separately. You may have to do it more than once.
But don't you do like the quotient rule?
No, you treat them as separate functions.
Okay.
That's the whole point of this here. We'll do another example 4 here. Try to get this. So again, going back in time, beginning of the course, you put 0 in for x. 1 minus cosine of 0 over 0 squared. You get 1 minus 1, which is 0 over 0. 0 over 0 is indeterminate form. So you take the derivative of the top, just the top separately, like just treat it like it's its own. So the derivative of cosine is minus sine. So the derivative of 1 is 0. Yeah, so you get positive sine x. That's not great, but that's okay. 2x. You do have to bring the limit down. Don't forget to write the limit. You do it again. You're like, all right, sine of 0. Try it again, 2 times 0. But again, you get 0 over 0. So you take another derivative, the top and the bottom. And you do this indefinitely until you get something that does work. And it really doesn't take that long. So now you're okay. Cosine of 0 is 1. So 1/2 is your answer.
Okay. Wait. Okay,
Well,
so for the denominator,
yes,
the derivative is 2x,
that's
right?
correct. That's correct.
So then when you plug in 0,
2 times 0 is 0.
x. So then on the below that, where'd you get just 2 from?
You take yet another derivative. Derivative of sine is cosine.
Oh, okay.
Derivative of 2x.
Easy.
You keep doing it until you get something that is an indeterminate form.
Okay. Okay, yeah, that makes sense.
All right. Now, for example 5, I find it's better to just do the problem and then go back and compare your work to theirs rather than trying to find the mistake. Plus, it'll give us more practice using L'Hopital's rule. So this is 0 squared over e to the 0 minus 1, which is 0 over 1 minus 1. It's 0 over 0. It's indeterminate form, right? So you got to take a derivative. What's the derivative of the numerator? It's 2x. Derivative of the denominator is just e to the x, okay? And so you try it again. You're like, all right, let's just try it. 2 times 0 over e to the 0. That's 0 over 1. Is that okay?
No.
Are you sure? 0
Well,
divided
that's
by,
0.
yeah, and that's good. You're done.
So only if it's undefined.
That's right. Or not necessarily undefined, but indeterminate form. If it were 1 over 0, that would be a problem. It would go to an infinity. But in this case, it goes to 0.
Okay.
So the reason I like doing it this way is because then you can and you almost want to cover up what's on the paper so that you're not biased by it. But you can see the mistake here is that they take yet another derivative, which they didn't need to, because when you try 0, it works. You get 0 over 1. You're in good shape.
Okay. So find the mistake. What does it mean by the string of equalities?
The each piece is supposed to be equivalent. So you want to show where the break in the link is. And these are okay. This is okay. This is the bad one right here. You want to say that again?
Okay, so just the derivatives.
Yeah. You don't need the derivative because you evaluate it at 0.
Yes. Okay. I got it.
Okay. So now we're looking at example 6. This one's better done graphically, but I know you can't graph them. Okay. So you get some problems here. The main one is like you don't have division. Okay, so you have to like do something. So one of the things you can do is take the natural log. So you can take the limit as x approaches 0 from the right of y, and y is really sine x to the x power. And then you can take a natural log of both sides. So this becomes x natural log of x. I'm sorry, x natural log sine x. Like that. Is that okay?
But what's the purpose of that?
We have to turn this into something over something.
Okay.
Sorry, I just want to check because this one is weird. I want to make sure I've got the right notes on this one. Just give me like 2 minutes or a minute here to just. You don't happen to have the notes from class, do you?
No.
Okay. All right, we'll just keep going here. So the Sorry, I'm just trying to debate how to go about doing this. Okay. So we're transforming this thing, and on the right here, you can rewrite it as natural log of sine x over 1 over x, which is really odd, but that is what is needed here.
Mhm.
Now, this is a new indeterminate form. Okay, because if as it approaches 0, sine of 0 is 0. The natural log of 0 is minus infinity. 1 over 0 is also infinity. So it's another indeterminate form.
Okay.
So you have to take a derivative of the top and the bottom. So the derivative of the top is 1 over sine x times derivative of sine is cosine x. The derivative of the bottom is minus 1 over x squared.
Mhm.
And now we can play around with kind of manipulating this thing a little bit. I don't like where this is going. I still, sorry, I feel like this isn't quite right. I just want to check if there's sometimes like a weird substitution. Did I do this right? Okay, let me come back to this one
Okay.
if we got time, because there's something else. This isn't working out, and I don't know I don't know how to get us there without wasting a lot of time. So let's go to the other lesson and start on some of that stuff. So let's go right to the derivatives.
Okay.
This will be a good review here for this. And then we can come back and do more L'Hopital's rule stuff if we need to. All right, find the derivative of arctangent 3x plus 1. So there's several derivative inverse rules you have to know. And by now you've probably figured out that like the x that's in this one means like that it's really this 3x plus 1. Is that something you remember?
Wait, can you say that again?
So the part I'm like, let me color code it here a little better. It's really this x really represents anything that's in parentheses here.
Okay. So you have to plug that in, so it's 3x plus 1 squared.
Yeah, but there's a bit more because these are all multiplied by the chain rule. So it's 3x plus 1 squared plus 1 times the derivative of the inside function, which is 3.
Okay. But on the rules, it doesn't even say the
So there,
multiply it by the derivative.
so it's really a chain rule derivative. It's 1 over u squared plus 1 u prime. They're all chain rule derivatives.
Okay.
Okay. So any questions on that before we move on to the next example?
Yeah, that makes sense.
Okay. Sorry, I lost my place. There it is. Okay. All right, so the next one here, example 2, more problems here. So the way to look at this one is that it's a power rule followed by a trig rule followed by a chain rule.
Okay.
So the derivative starts with the outermost function 3 sine inverse 5x to the fourth to the power of 2. Now you take the derivative of arcsine. So let me grab that again here and snip it down. So the derivative of arcsine is 1 over square root 1 minus x squared, but that x refers to whatever's in parentheses. So when we're taking our derivative, it's 1 over the square root of 1 minus 5x to the fourth squared, because that's the part in there. And then you have to multiply by the derivative of 5x to the fourth, which is times 20x cubed.
Mm-hmm. That makes sense.
Okay. So that's everything for that one. The next one here is natural log, okay? All right, so the derivative of natural log is 1 over what's inside the parentheses. Okay. Then you have to take the derivative of secant inverse. Now I don't know any of these because I would look them up, but I guess you'll have to memorize these. And there are some patterns to take advantage of. They're kind of all similar, you know, they've all kind of got the same form, but there's, you know, little wrinkles between them. You should know that secant and cosine kind of match in some ways. So there's some things there you can leverage. So this becomes 1 over the absolute value of x squared square root of x squared minus 1. And then you have to take the derivative of the innermost function x squared times the 2x.
Okay, so then we tend to simplify.
Usually you can leave them like this.
Wait,
It depends on the teacher.
why do you take the derivative of the absolute value instead of the square root?
I'm putting x squared in for x in this. So let me like x squared is going in for x there and there.
Okay.
And you should ask your teacher if you need to simplify or not.
Okay. Yeah, okay. I think I get that.
Okay, great. These are really tough, by the way. These are kind of out of scope for AP calculus. These won't be on the AP. The L'Hopital's rule will be.
But the other thing won't.
The trig inverse, very rare. Use this in calculus 2, not in calculus 1.
Okay.
But I mean, not that helps. So we got to take a derivative here. Always helps to have these handy. Let me snip these down again so you've got them. You're looking at this. So the derivative is with sine, it's 1 over the square root of 1 minus x squared. So 1 over the square root of 1 minus x squared. But then you multiply by the derivative of the inside function, which is 2x. So this is all the derivative here. Check and see if that's okay or not.
So the sine -1. Yeah.
Okay. Now the next thing is that they want you to evaluate their derivative at 1/2. So 2 times 1/2 in the numerator. Square root 1 minus And so it's really x to the fourth now. So we're going to do 1/2 to the fourth power. And so this becomes 1 over square root 1/2 to the fourth power is 1 over 16. So it's 16 over 16 minus 1 over 16, which becomes square root of 15 over the square root of 16, which is really 4. So this becomes 4 over the square root of 15. And then you rationalize the top and bottom by multiplying by the square root of 15. 4 square root of 15 over 15. None of this is calculus. The calculus ended right here. You're just putting the number into the equation.
Okay. Okay, yeah, so all of it's really just plugging stuff in for this, right?
Yep.
Okay.
Yep.
There's
another example we can do. Okay, so we're going to integration. Integration here. So your eyes should be drawn to the fact that there's a u substitution potentially, because the derivative of cosine inverse is 1 over, u prime here is 1 over the square root of 1 minus x squared. There's actually a negative in there. Yeah. And you should be thrilled. You should say, oh my gosh, there's that's in the integral. So your u substitutions are done when the derivative is already in the integral. Like that's a good sign.
okay.
So we start replacing what we know. So we know that it's natural log of u over u. Now we got to solve this for dx. Dx ends up equaling negative du square root of 1 minus x squared. So we're going to put that in here. Negative du square root 1 minus x squared. We're replacing dx all over square root 1 minus x squared. And you're like, all of a sudden, you're like, all right, that's great. I see some cancellations. These cancel. And the integral is much, much simpler. It's negative natural log of u over u du.
Okay. And so, okay.
So we're still not done, but we've made progress. This requires an additional substitution. Kind of the same deal. Like let's let v equal the natural log of u. So dv is going to equal 1 over u du. And you're thrilled again because that's in the integral.
Mhm.
So when you solve this for du is u times dv. So this becomes the integral minus v over u. Du is u times dv. And you're like, hey, got another cancellation. That's great. So you've got integral minus v dv, and you're finally ready to find the antiderivative.
Okay.
So the antiderivative here is minus 1/2 v squared plus c.
Okay.
But that's not the final answer because you have to back substitute all of the things you've been doing. So your v is really natural log of u. Okay, so you said, okay, v is really natural log of u. So this is minus 1/2 natural log of u squared plus c. But u was really, I'm going to go back, cosine inverse of x. So it's minus 1/2 natural log of cosine inverse of x squared plus c.
Okay. But how do we solve for C?
We don't have any information to solve for c. It's just a constant of integration. You'd have to be told that, at 0,
You
y
just leave
is,
it like that?
something. What, say that again?
So you would leave it like that?
Yes. Yes, this is your final answer.
Okay, that's a really long, like hard question.
Yes, this is. It's in calculus too. You also won't see that on the AP exam. Okay, here we go. This is still part of example 4, another integration. All right, so you should always sort of be looking towards u substitutions. Your u here is arctangent of x. And the reason is its derivative, 1 over x squared plus 1 dx, is already in the integral.
Okay, so this is like everything combined.
Yes, yes, yeah,
U sub, U sub, derivatives,
everything, yeah.
integration, everything.
So we've got x squared plus 1. Dx is really du times x squared plus 1. So we're gonna substitute for that, like that. And you're like, hey, another cancellation. That's great. Becomes just the integral of u du, which is 1/2 u squared plus c. But you have to back substitute, say, oh, it's not u, I'm using tan inverse. U is really tan inverse of x. So it becomes 1/2 tan inverse of x squared plus c.
Mhm. Okay, so that's all.
That's all the examples that she provided, or your teacher provided, for there. I would recommend doing more L'Hopital's rule, or more, I guess, integration or derivatives. I don't know. What would you like? We've got some time left.
Do you think we could go back to the other question or?
Yeah, I mean, so let me show you the graph of it. I was looking at, I couldn't find the exact problem. I found one similar, and it's different functions, doesn't work out as nicely, but here's the graph of it. So we know that it does end up equaling 1. So that was the
Mhm.
limit as x goes to 0 from the right, sine x to the power of x. It might be a root. See, there's another, that's where I was wondering about the notes, because you can also find the limit as x goes to 0 positive sine x and use this root property of its x to the 1 over x power. I'm really not sure though. I would really prefer to defer to whatever she's doing in class. Or I can keep looking. Problem was the way I had transformed it didn't work out nicely, which means I either transformed it wrong or there's another transformation I'm not seeing.
Mhm.
So what would be best? Would you like me to spend some more time trying to figure it out?
Yeah.
Okay. Actually, this one's kind of similar. Let me see if I can quickly get okay, we'll try that. I mean, this is the only path we can go down. So you set y equal to sine x to the x, you take the natural log of both sides, and you get x natural log sine x like that. And then this is the issue, is you have to rewrite this, and you're really limited with what you can rewrite it as, because you need a top and a bottom. So that's where I was getting stuck here, because the only way I know to rewrite this is 1 over x, but we could actually, I take that back. We can rewrite it the other way. We can write it as x over 1 over the natural log of sine x, like this.
Mhm.
So if we go that direction, when you put 0 in for the top, you get 0 over 1 over infinity, which is 0. So the reason is sine goes to 0, the natural log of 0 is negative infinity. That gives you your indeterminate form that you want. It really does give you the 0 over 0, which means that you can take the derivative of the top and the bottom. So you take derivative of the top, 1. The bottom is quotient rule, kind of. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, 1 over sine x times derivative of sine is cosine x, all over the bottom natural log squared of sine x. Okay, and now what we can do, okay, so this becomes, just clean this up here, 1 over minus cotangent x over the natural log squared of sine x. And if that goes up here, will that work? It will not work, but it is another indeterminate form. So this we change to natural log squared of sine x over minus cotangent x. And as x approaches 0, sine goes to 0, natural log of that goes to minus infinity. Cotangent at 0 is really cosine x over sine x. That also goes to infinity, so you end up getting infinity over infinity, so you have to take yet another derivative. So on the top, it's 2 natural log sine x times 1 over sine x times derivative of sine, which is cosine x. There's your cotangent. Derivative of cotangent is cosecant squared x, maybe?
Mhm.
I haven't used that one in a while.
Wait.
Is it cosecant squared? But I think it's negative, so it ends up being positive cosecant squared.
Yeah, that sounds right.
It's not cotangent, is it?
I have no idea.
Yeah, I'm just checking real quick because it's everything's gonna get messed up. Yeah, it is. Okay. So now, which is finally something better, I guess. Just trying to figure this out. I feel like, again, I've gone in the wrong direction because it's not I'm surprised it would take more than 2 steps. Let me try one more here. Looking at one more thing here.
Okay.
This one says it does not exist, but it does from the right. It does exist from the right. See, this is hugely problematic here. Because we got to eventually get rid of that. 2 natural log sine. Oh, those don't cancel. Cotangent x over cosecant squared x. Does anything cancel here? Cosine over sine, 1 over cosine. I'm still just not seeing it.
Neither am I.
Yeah. The graph though does show that it converges, so there's something here. I would just ask the teacher. We can do some other problems if you would like. That would be more useful.
Is there any other problems on the
No, we've
project?
done we've done everything on both. I'm sorry, we did not do kind of these starter evaluating, finding the value of these inverse trig functions. So we can do that. All right, so find the value of tangent of cosine inverse of 3/5. So the idea here is you let theta equal cosine inverse of 3/5. You take the cosine of both sides and you draw a triangle. And you get 3, 5, and using Pythagorean triples or Pythagorean theorem, you find the other side is 4. So the tangent of theta, that's what's inside parentheses, becomes 4 over 3.
Mm-hmm.
Any questions on that?
This is like trig.
Yes, that's why I didn't do it at first, because it's not
This is more
calculus.
like calc, right?
Yeah, so let's do the last one. It's kind of like that.
The second one, it's just x though, right?
Yes.
Okay.
So this one is let theta equal sine inverse of 1/2. This isn't completely true. There's domain restrictions. It's from minus pi over 2 to pi over 2, but
Mhm.
that's a side note. So the sine of theta equals 1/2. So you draw another triangle. 1 over 2, and then this is the square root of 3. So your cosine of theta is the adjacent over the hypotenuse.
Mhm. So that's it.
That is it.
Okay, I think I get it. Yeah. I
Okay.
think with the really like long and complex ones.
Say that one more time. I'm sorry, I didn't quite
I just
follow.
don't get the really long and complex ones.
Yeah, the ones where you're integrating double U substitutions kind of insane, but that's your teacher. You just piece it together. But this kind of stuff is not on the AP. It's different stuff. It's more like what we were doing yesterday. Those are AP stuff.
Mhm.
This is more like what you would see in calculus 2 in college or next year, maybe.
Okay, so okay, then I get it.
Got a couple minutes left. Is there anything else you would like us to cover
Mhm.
tonight?
Nope.
All right. Well, we can certainly stop here.
Yep. Thank you.